Okay, so let's get started with this last session. So I would like to introduce our first speaker is Margherita Mazzera from Heriot Watt University. And she'll be talking about new platforms for integrated solid-state quantum memories. Please take it away.
Yes. Hello. Good afternoon, everyone. Many thanks, Cecile, for introducing me. And also, I want to send a big thank to the organizers of this virtual conference for the amazing work that they did to put together this meeting. So as you said, I am currently at Heriot Watt University, starting a new group on integrated quantum memories. But because I just recently joined, I'm going to talk to you today about some work that we did in my previous appointment at IPFO, the Institute of Photonic Science in Barcelona. So this is the group as it looked when I left, and I want to thank especially the people highlighted in orange, which who are those who really did the job that I'm going to present today. I also want to thank our collaborators in Milan who are preparing the waveguide chips that I'm going to show you in a while. We have seen earlier in this conference how quantum memories are fundamental building blocks for quantum communication and quantum computation protocols, because they act as interfaces between stationary and flying qubits. In particular, we've also seen earlier today that for quantum networks application, where the idea is to encode the quantum information, so map it into the state of single photons, they are very important for the realization of the so-called quantum repeater architecture, to overcome the problem of loss of information due to the loss in optical fibers. Quantum repeater architectures is essentially based on the idea of dividing a transfer line into smaller segments, each including a pair of quantum memory. Then an entanglement is created in each independent link and stored in the quantum memories until all the independent links are entangled, and then released to extend the entanglement over the whole transfer line. Of course, this requires the ability of creating, storing, and transferring entanglement. And I'm going to show you today a particular protocol that we are aiming at implementing. It is based on a proposal from the group of Geneva back in 2007 that is inspired by the seminal paper of Duan-Luc, Thirac, and Soler of 2001. This originally involved the generation and the storage of photonic entanglement by means of atomic ensembles. In the Geneva proposal, instead, the creation and the storage stage are separated, and this to relax a bit the requirements of each building block. In particular, we need a pair of photon pair sources, each generating one photon compatible with a quantum memory, with no really restriction on the frequency of the quantum memory, and the other photon at telecom wavelength, such that it's easily transferred over long distances. The quantum memory on the other side has to feature high efficiency, long storage time, and on-demand readout, at least. Then the higher is the multiplexing capability of the platform that you choose, the higher is the entanglement rate, distribution rate that you can achieve. So in this talk, I'm going to focus to show you our approach towards the development of this, of the ingredients of this quantum repeater scheme, starting from the solid state quantum light source. Now, if you have to create a pair of photons widely non-degenerate in frequency, most probably the best mechanism is spontaneous parametric down conversion, of which we have seen already this morning some exceptional examples, except that here we have a further challenge, that is that of matching the frequency and most of all the bandwidth of the photons created to the bandwidth of the atoms that we are going to use to store these photons. So our strategy was to place our nonlinear crystal, a PPLN crystal, into an optical cavity. Then we pumped this crystal with a light at 426 nanometer to create a photon pair, where one photon, the idler, is a telecom wavelength, and the other is in the visible range as 606 nanometer. That's compatible with the quantum memory that we have. Of course, because the crystal is placed inside an optical cavity, we will have enhancement of the creation of the pair creation only at the frequencies supported by the cavity modes. And so if we design properly the cavity, we will, with this trick, we will end up with a very narrow band photon pairs, which means also with very long coherence time, and very high non-classical correlation. So I'm showing you here an example of non-classical correlation between the idler and the signal photons, where you can appreciate a coherence time more longer than 100 nanoseconds. At the same time, if we measure heralded autocorrelation of the signal photon, we also see quite marked anti-bunching, which means that the quality of our photons is very good. So what are we doing now that we have created these photon pairs? Well, we want to store one of the two. So we take the telecom photon and we use it as a herald of the presence of the visible photon that we then send to our quantum memory. The platform that we choose for the quantum memory is insulating material. It's a crystal, yttrium silicate crystal, doped with a big number of praseodymium ions. The choice of these ions is motivated by the fact that it's motivated by their very convenient energy level scheme. In fact, these ions have 3-fold ground state originated by the spin hyperfine interaction. And all these 3 ground states are connected quite efficiently with the same excited state through electronic transition that also has very good coherence properties, at least 150 microseconds. Now, each atom in the matrix retains some very good coherence properties typical of the isolated atom. However, if we look at the crystal as a macroscopic object, because each atom sees a slightly different environment, the crystal will have an inhomogeneously broadened absorption profile that actually we can use to tailor some very specific structure that will be useful for the storage protocol. Now, assume that you have an ensemble of atoms with the electronic transition and which is inhomogeneously broadened. So if you have a single photon absorbed over this transition, the state of the single photon will be mapped into a coherent superposition of atomic excitation. But because each atom is slightly detuned with respect to the photon, each of these atomic excitation will start to dephase and quickly the coherence will be gone. Unless you are able to tailor with some optical pumping schemes, so optically, periodical structure in the inhomogeneously broadened absorption profile of the ensemble. Now, because the spectrum of the atoms is periodic, then this means that also at periodic time, the atoms will rephase, giving rise to a collective and coherent emission is in the forward mode that we call atomic frequency comb echo. The atomic frequency comb is the structure that we create here. Now, despite the fact that there's a delay between the absorption of the photon and the release of this collective emission, like of this copy of the original photon, this protocol is strictly speaking not a good quantum memory protocol because it's not on demand. But if your atoms do have another ground state, and if you are able to empty it, then before the collective re-emission, you can transfer by means of optical pulses the excitation to the ground state, and then leave it there for an arbitrarily long time, taking advantage of the fact that the storage, the coherence time of the ground state is much, much longer. In some cases also it can reach hours. And then you can achieve, you can have an on-demand retrieval by just sending another optical pulse and obtaining a so-called spin wave echo. Now, this is an on-demand protocol for the storage of single photons. It gives access to long storage times, and it's also inherently temporally multimode. So if we now take these two ingredients, the photon pair source and the quantum memory built with this protocol, and we put them together, we can actually demonstrate to be able to build, let's say, half a link of half an elementary link of this quantum repeater scheme. And this is what we did in this paper here. We took the photons and we stored one of the two, the visible photon, into an atomic frequency comb memory. And we also demonstrated that after the storage, we could maintain, we could have a non-classical correlation between the telecom photon and the stored and retrieved single photon. However, this is a very complex experiment, and the setup is taking almost 3 optical tables. And this is not very convenient in terms of, so in view of implementing real life quantum network protocols. It would be very nice if you could take all the object here included in this bubble and shrink them down to the dimension of a coin, for example. And this is why a few years ago we started exploring ways to develop integrated quantum memories. Our approach is to create waveguides in our crystal by means of femtosecond laser micromachining. These techniques relies on the permanent modification of the crystal in the following way. So we create, as you can see here on the right, we create some damage tracks along the crystal. And if we cut the crystal, if we cut a section of the crystal, what you can see is that actually light can be guided within the 2 parallel damage tracks due to a slight increase of the refractive index. However, if you decrease the dimension of these damage tracks, you also notice that the insertion losses are increasing dramatically. And I'm sure you agree with me that it doesn't really make sense to have an integrated quantum memory where you lose more than 90% of the light just in coupling it in the waveguide. And this is the reason why in recent years we instead studied another kind of femtosecond laser micromachined waveguide, the so-called type 1. This relies on the use of much lower power for the fabrication. And in this new regime, the increase of the refractive index will happen in the damage track. This means that this time the damage is the region that is guiding the light. As a result, we will have much smaller waveguide modes and with a much better, much lower insertion loss due to the high quality of the track. Now, surprisingly enough, because practically what we are doing is damaging the sample, it turns out that the atoms dispersed in the material still retain their coherence property for long enough to allow us to prepare our famous atomic frequency comb structure and to store the single photons coming from the quantum light source. I had to say, though, to be fair, that this echo here, these retrieved photons here, do not come from the full spin wave storage, so it's not yet on-demand storage. However, even if this is only implemented at the excited state, we can still achieve non-classical correlation between the telecom photon and the stored photon for storage time 100 times longer than in previous realization. Now, if I have to be honest, at this point, we do not yet outperform what we have achieved in the bulk. However, if you let me in my very last slide, I will demonstrate you that there are actually aspects in which we do outperform the bulk. Now, this is a reminder of how our source is done. We have our PPLN sample in the cavity, in the optical cavity. This means that by having the optical cavity, the spectral content of our single photon is spread over multiple frequency mode, of which we typically just use one because we prepare our atomic frequency comb in a very reduced spectral region, about 400 megahertz. But if we wanted to use all the photons actually coming out of the quantum light sources, which are spread over around 15 spectral modes, separated by the free spectral range of the cavity, this would be absolutely impossible in a bulk setup, because we would need either crazy high power or extremely long preparation time. However, because we are in a waveguide, and due to the confinement, the light and the atoms are interacting much, much more efficiently, we can actually prepare our atoms, so do the optical pumping schemes with power around 100 times less than in a bulk realization. This allows us to simultaneously prepare 15 atomic frequency combs throughout the inhomogeneously broadened profile of our quantum memory ensemble. And this is the very last result in which I show you the whole spectrum of the quantum light sources spread over 15 spectral mode. And here in orange, let's say it's the photon correlation after one of the two photons is stored in our quantum memory. So now we do actually outperform the bulk implementation, because for the first time we are able to store the whole spectrum of a single photon. Now, to wrap up, I have talked to you about a specific protocol for the realization of quantum repeater based on multimode sources of entangled photons and multimode memory. And I have shown you our efforts towards the realization of these multimode sources and multimode memories. But most of all, I have demonstrated that thanks to the integration into waveguide structures, we can achieve spatial and frequency multiplexing that wouldn't be possible in a bulk demonstration. And before thanking you for your attention, I want to advertise that because I'm starting a new group, I have PhD and postdoc positions available. So if you're interested, just contact me. And finally, thank you for your attention.
Okay, thank you very much, Margarita, for that interesting talk. It was great. Thank you for that. So Actually, one question that has just come in is if you could comment on a bit more on the reasons of using that specific defect system from Jorge Monroy, sorry.
Yes, for the defect system as a quantum memory, I guess.
Yeah, probably.
Yes. So, well, first of all, it is solid state, and we do like solid state platforms, exactly because they are compatible with integration. Let's say integration is much easier. Then, as I said before, it has this very nice, very convenient energy level scheme. You have this 3 ground state here, which have very long coherence time. In this platform, specifically with these ions, this can reach a couple of minutes. And this is the ultimate limit for the storage of quantum information, of single photons. However, with very similar platform, but just changing the optical active ion here, you can actually achieve coherence time of hours. And then it has also already demonstrated very high efficiency. So it's a very convenient platform for the fact that it fulfills these requirements of high efficiency, long storage time, and multiplexing capacity that are required for quantum repeater schemes.
Thank you. Another question is, do you also use integrated light sources?
At the moment, not, but it's something that we want to explore using the same platform here. Actually, there are schemes. Well, the DLCZ scheme that I commented on in the introduction of my talk, that in which you create and store photonic entanglement with the same system, so at the same time. And we have demonstrated this with this very same crystal in a bulk demonstration, and there are prospects to try and do that also in waveguide design.
Okay, I think we have time for one more question. So this is anonymous, and it's, does the storage time of the quantum memory ion benefits from the millikelvin temperature? And how much improvement in comparison with 4K temperature?
Yeah, so in this specific crystal, so we are working at around 3 Kelvin. And this specific crystal, it doesn't really need millikelvin millikelvin temperature. In terms of coherence, at 3 Kelvin, we are already quite close to what you would achieve at sub-Kelvin temperature. In other crystal, with same platform, but other active ions, for example, erbium, then you would need much lower temperatures, yes. But with this specific ion, you don't really need extremely cold environments.
Okay. Well, thank you very much again for that great talk. We'll continue with the questions on the Slack channel.
Yes.